All right, welcome to lesson 5.6, Advanced Algebra Notes, Inverse of a Function. Whole lesson focusing on inverses here. We'll look at how to write inverses, verifying that two functions are inverses, graphing some inverses. Um, so we'll start here a little bit with just kind of some old school skill work. Some of it's just recognizing notation. What's it? What are we being asked to do? So we did add this to our notes, solving equations for x, which is something that I know you've done in the past, but it'll look just kind of looks different with some of the notation. So just big things to remember that when we see f of x, which is usually representing the output of a function, we also associate y with the outputs, right? X are inputs, y's are outputs. So that's gonna be part of what we'll do. Basically, this is kind of just saying, long story short, um, instead of using, basically switch your f of x to say y equals, and then just get the x by itself, solve for x. So let's jump in here and kind of practice that. It's a skill we need to be able to find inverses. And I know we just talked about inverses, but uh, or we haven't even said what an inverse is. But this is kind of the skill that's going to be kind of the common thread for everything we do. So let's take a look at what we're being asked to do. Writing a formula for input of a function. So we've got this function. Let f of x equal 2x plus 3, a linear function. Fine, great. Here's the part that sometimes people get confused with. Solve y equals f of x for x. So, like I said, what that's telling us to do for part A here is take this f of x, solve it as, or essentially replace our f of x with y equals 2x plus 3. So that first part was kind of just swapping my f of x for y. That's all I did was change this to y. And then now solve it for x. That just means get the x by itself. So there's two steps here. I got to get rid of two numbers, the 3 and the 2, right? So we would subtract a 3. I'm going to try to I'll talk about the steps without showing every step for step. So I would subtract a 3 from both sides. I'm just trying to make sure I can keep it to a single screen without having to scroll a ton. So y minus 3, I've subtracted a 3 from both sides. I'm still going to do it in multiple steps, though. So I've gotten rid of the 3 on the right side. The x is still not by itself yet. So to undo a 2 times x, we would divide both sides by 2. And we can leave it just like that. Our 2's would cancel. So we could say x equals y minus 3 over 2. Kind of scrunched it in there a little bit. Just so you know, depending on kind of what your background is and how you'd solve it, some people might, on this step right here, I'll just kind of show like an alternate take. You might, instead of dividing by 2, some people might multiply by 1/2 to get rid of the 2. So obviously on the left side, you would have been multiplying by 1/2 that you could distribute here and here. So kind of like an alternate take, which we'll see actually a few times, that just kind of looks different but mean the same thing. 1/2 y minus 3/2 equals x. These mean the same thing. I hope everybody kind of recognizes that or sees that. I'm not saying you have to have yours simplified to this. But if we see this, know that those they mean the same thing. Okay, so that's part A, is just solve y equals f of x for x. And then the last part, when it says, all right, now basically use what we just found, we can use this one right here. Find the input when the output is -7. And we talked about that a second ago. That, remember, our inputs, we're going to look for the input when the output is -7. That's why it's nice to have this set up that way, where I can plug in an output here for y and see, well, what must we have inputted to get that output? So I'll come up here and do part B. It's kind of hopefully as simple as taking this -7 and inputting it, plugging it in essentially for where the outputs go. I know it's kind of weird to say it like we're going to input it where the outputs are, and we're going to calculate the input, but that's what we're doing. So I've taken the -7, I plugged it in for y, and what do we get? -10 over 2, which is -5, which is equal to x. All right. So there's some skill there, just as far as I just want to make sure we're sharp with some of that stuff that you hopefully did a lot of in an Algebra 1 class of rewriting equations. We're kind of just tying some of the function notation to it. Let's practice a little bit. That was a linear example. I have another linear example here, but then also a quadratic, a cubic function. So it just, you potentially have some different some different things that come up. So let's do them, pause it. You guys try them as always, and we'll run through them right now. All right, so first step is just kind of replace my f of x with y. This is a nice one. Whoops, I'm writing what I'm about to try to do. X minus 2. How would I get this x by itself? Solve for x, right? We're going to solve for x. We'd add 2 to both sides. So this one's really nice. I end up with y plus 2 equals x, and that's it. The last part, when it says then find the inputs potentially when the output is 2. So that's, again, kind of simple in this one in the sense that we're just plugging in 2 plus 2 equals x. So 4 equals x. The only thing I don't like is, Mr. Always got to have things the right way. I like having the x on the other side. You could obviously write this as x equals 4, 4 equals x, but whatever. I won't lose any sleep. Okay, here we go. Let's up the difficulty level just a little bit. I don't think it's terrible. We've got same kind of first step, y equals 2. Maybe it's helpful to put the dot in there to remind ourselves that this 2 is not connected for life to this x squared. It's something that we should get rid of at this point. So we'll divide both sides by 2, get y over 2 equals x squared, right? So make sure you get rid of that. I know there's sometimes people want to square root right away and just say, let's square root both sides. Well, then you got to square root this 2, and not that it would be the end of the world, but let's get it to the other side. And now I say, let's square root both sides. Don't forget, very, very common mistake here. Whenever we solve an equation using square roots, and that's what we're doing, we're solving an equation right now, we get 2 solutions. We should set ourselves up for two solutions. So I kind of got tight on space there, but I just square rooted both sides. Here's my new left side. Y. We don't really have to do anything else other than just kind of keep it underneath the square root symbol. But on the on the right side, our square root got rid of our squared and left us with our x. But yeah, don't forget about that positive, negative. If you're looking at this thinking, why is he really circling his answer, saying that's it? I know we talked about earlier simplest radical form, not leaving fractions underneath there. For the sake of this unit, this section 5.6, just to keep things a little bit simpler, I'm okay with leaving this here just as long as you've got your x by itself. I'm okay with that. Okay, so yeah, it is what it is. Last part on this one, let's plug in our 2 here. So here's where we'll see it. I'll probably have to scroll down a little bit. Positive, negative, square root of 2 over 2 is equaling x. So the square root of 1 is 1. So the positive, negative 1 equals x. So we do end up, that's why there was that little parenthesis s on the directions, right? Outputs, potentially. Positive 1 and negative 1 equals x. So if we go up and look, it's one... This one we didn't hope, most people I'm sure didn't check that one. But we could go back to the original problem, plug this in for the input, and see what the output is. So if I plug in a 4 minus 2, sure, it's 2. Here, if I plug in a 1, 1 squared is 1, 1 times 2 is 2. Sure, I get an output of 2, but so is negative 1, right? If I plug in a negative 1 here, I square it, I get 1, 1 times 2 is 2. So there are 2 outputs on that. Am I ever going to remember that? I'm just joking. You guys are good at that. All right. Last one. Just a cubic. Nothing like crazy here. It's very similar to this last one. Although there's one slight thing here. Let's see how we do. So y equals the opposite of x cubed plus 3. I'm getting tight here on the edge, but I think we can manage. Let's get the 3 out of here. So y minus 3 equals the opposite of x cubed. I'm not ready to cube root yet. Let's get rid of this. Maybe it's helpful to put a little minus 1 there to remind yourself that, you know what, I can get rid of that the same way we would always get rid of something being multiplied by a variable. On the left side, we can simplify it. We don't have to leave it as a fraction there. It's really just going to change the sign. So it's going to leave us with the opposite of y plus 3 equals x cubed. Okay. Now we're at a spot where we should cube root both sides. But what's the difference between number 3 here and number 2? When we cube root to solve an equation, it doesn't matter. We can just leave it. Like, we don't need two solutions, what I'm saying. I shouldn't say it doesn't matter. But whenever we odd root to solve an equation, there's only one solution. So that's actually where we end up finishing up. The opposite of y plus 3 is equal to x. All right, so just like the last one, there's that finish. Let's plug in. So we're going to only have a single solution on this one. If I plug in a 2, I believe is what we've been plugging in. Whoops, this should say cube root there. I almost forgot that. Cube root of the opposite of 2 plus 3 equals x. So it's going to be a 1 again underneath there. The cube root of 1 is 1. X equals 1. Are we good? Let's take a look. Just do a very quick check. Again, for the sake of video notes, I'd rather be all right here. 1 cubed is 1, negative 1, or the opposite of 1 is negative 1, plus 3 is 2. Yeah, we're good there. So we should end up with x equals 1. All right, so that's kind of just a review of some old skills of rewriting, plugging in stuff into functions. Let's get into what the heck are these inverse functions. So when we start talking about what is an inverse, this is all just kind of Mr. Kroll just using his words to excuse me, make things a little simpler to understand. Inverse functions are functions that undo each other. So an example might be just real basic f of x equals x squared, right? A quadratic function, and g of x equals the square root of x, right? And we use those operations. We just used them a second ago. How did we get rid of squareds? Right? How did I get rid of the squared? I square rooted. How did I get rid of a cube? I cube rooted. How did I get rid of even subtraction? I added. So those are inverse operations. So they play right into it here, that inverse functions essentially undo each other. And by doing that, an inverse or a function and its inverse are going to change the roles of x and y. And by doing that, by kind of understanding that x and y essentially kind of get switched around, right along with that, domain and range also gets switched around. So the domain of this one becomes the range of this one. I'm trying not to confuse myself here. The domain of this function would become the range of this function. The range of this function would become the domain of this one, and vice versa. All right, it's a little bit kind of talking domain and range there. I sometimes lose you guys a little bit, but yeah, so those are some bullet points there worth noting. That's what inverses are. We'll talk about how do we actually come up with them and how do we write an inverse. But those are some of the key features of what an inverse is. Graphically, when we graph a function, let's look at these. This is a perfect example here. So here's my original function. We'll talk about this in a second. The original function is a linear function, f of x equals 2x plus 3. All right, we plug in -2 to 2, we plot some points, graph it, boom, there's f of x, or there's function f. The inverse, here's what the inverse looks like, and you can see there's different, look at that, we talked about inverse operations. We went from +3 to -3. We went from ×2 to divided by 2. So there's all that stuff's at play there. That's where that skill is going to come in, that rewrite stuff. But here's g of x, and I start plugging x's in, I get these weird numbers here, and wait a minute, hold on, why did you plug in -1, 1, 3, 5, 7 to plug in? Well, look with the arrows, and I know the arrows here are showing what happened. The output of this one became the input of this one, where the input of this one became the output of this one. So we are literally switching the roles of x and y. These x's became y's, these y's became x's, and vice versa. Because of how that works and what's going on there, the graphs end up being a reflection over this line y equals x. So this point, you can see it right here. We don't have to re-say all of them, but this point is 2, 7. If I reflect that over that graph, that becomes the point 7, 2, which is out here. Okay, and that's going to be true for all functions and their inverses. If you graph a function and its inverse, you'll see. So there's kind of a visual confirmation there that they're reflected over the line y equals x. All right. Okay, let's do it. So this is kind of our first one. This is kind of one of the big concepts of the lesson, is being able to find an inverse. So you get a function and say, okay, here it is. Find the inverse. Let's do it. We can do it. We'll do some steps here, but I honestly don't think they're not super deep steps. The first step, what I would say is just like we did before, replace my f of x with y. Well, let's say it maybe like as an actual step. What should we be doing here when it tells me to find an inverse? Let's just say switch or replace f of x with y. So then over here, maybe we'll do it then. Y equals 3x minus 1. Easy first step. We did it a bunch of times already. Replace f of x with y. Second step. This is where, like, what did we say was like the crucial feature of an inverse function? We switch the roles of x and y. So we are literally, when we're asked to find an inverse, we're literally going to swap x and y. So I go from y equals 3x minus 1 to x equals 3y minus 1. So far, I mean, it was just a couple switches, right? We switched f of x with y, and now I've flip-flopped my x and my y around. The last part is what we've done already a couple times today. Solve for y. Get the y by itself. So there's now here's where like the work kind of comes in now. Okay, which we can do that though, right? So like right now, how am I going to get this y by itself? I'd be adding 1 to both sides. Right, we're using what we would call inverse operations. And then I would divide both sides by 3. And we would say our inverse, here's our inverse. I'm just going to write it bigger over here so we can see it. X plus 1 over 3 is equal to y, or just flip the whole thing and say y equals x plus 1 over 3. There's our inverse. So it should feel familiar. We basically did that other than the swapping of the x and the y part. We did this 4 times already in the lesson. Okay, so we'll practice it, but that is definitely that's kind of the skill that we'll do on almost all the exercises here. All right, just to mention it, we didn't really add a ton of this in class, but when we start talking about nonlinear functions, okay, so just for example, we're looking at a quadratic parent function here in blue, or a cubic parent function, f of x equals x cubed. When I look at the inverses of those functions, we don't always end up with a function. Remember, a function's one output for every input, which the blue ones both are functions. But notice if I reflect this blue one over the line y equals x, like we said is going to happen, this resulting one kind of gets turned on its side a little bit, and this is no longer a function. Why? Let's just pick a nice number here. If I plug in a 4 into this red function, sometimes I get 2 for an output. Sometimes we get -2 for an output. So other than just kind of recognizing that you can go from a function and then the inverse not being a function, that's kind of all we need to recognize. Whereas in just side-by-side comparison, sometimes it does happen. It's kind of a cool looking graph, especially with the colors. But like my original cubic function, when I write the inverse of it, I get a cube root function, which is also a function, right? There's one input for every output, so we're still good. So it doesn't always happen that way. It's just sometimes you could run into not having a function, which for right now is kind of okay. All right, let's take a look here. A couple different things going on. Finding the inverse of a quadratic function. So our parent one, let's write it. Notice there's one kind of like caveat here where it's, okay, x has got to be greater than 0. That'll factor in on both parts when I write the inverse and when I make the graph. So we can't just ignore that, but we just want to make sure I point that out and that we see it here initially. So let's just start with the first part. The graph is almost like a totally separate entity. Find the inverse of x squared with x is greater than or equal to 0. Okay, fine. Step 1 we said was just to replace f of x with y. So y equals x squared. Step 1 done. Step 2, what? Swap my x and my y. Awesome. Step 2 done. And then step 3 is get the y by itself. So here we go. We're square rooting both sides of the equation. We just said this earlier, that when I square root both sides, I got to remember plus minus square root of x equals y. But hold on a second. You just made a big deal about Mr. Crow. You said you always got to go plus minus. Here's where this kind of factors in right now. Because this is a domain restriction, it's saying, okay, this function exists, but only for x's that are greater than or equal to 0. That also means that our range is going to, if the domain is restricted, the range is restricted. So the range is also numbers that are greater than 0 or greater than or equal to 0. So remember what we said. The range of this one becomes the domain of this one, of the inverse. So this one's range, which y's are greater than 0 or equal to 0, now became the domain of this one. So long story short, and I know I probably lost a few of you there, because of that initial restriction on the original function on f of x, we're only going to end up working with positive values, positive outputs on this, on our inverse. Okay, so hopefully that makes sense. Y equals the square root of x. Yeah. All right. So there's our finding their inverse. Let's graph it. Let's do the graph part of it. Like I said, almost totally separate. So I usually give you a table for this, but if I don't give you one, make one. So for f of x, all we're doing, I'm coming back up here. I'm looking at f of x and I'm saying, let's pick x values and plug them in there, square them, and what happens? As long as I follow this last part that says, hey, you can only pick x's that are greater than or equal to 0. Okay, fine. Usually that's a good one to start with. Like, let's pick x equals 0, plug it in, square it. Let's plug in 1. 1's a good one to plug in. If I plug in a 1, I square it, I get 1. Plug in a 2. Why don't we just stick with whole numbers around? 2, plug in a 2, square it. 2 squared is 4. We could go up. Why not? Just to have it in our table. 3, if I plug in a 3, 3 squared is 9. That's enough. I think we can make a pretty solid graph with that. 0, 0, 1, 1, 2, 1, 2, 3, 4. And we're off a little bit. We're way up here, 3, 9. But so we got like this half of a parabola. Fine. That's okay. And I mean, it is what it is. But make sure you're not like connecting this other half over here and saying, well, we just didn't draw these ones. We weren't allowed to plug in those numbers. Okay. So that's where that factors in on the graph. The last thing we got to do, I'll use red because it'll match up with our inverse. For our inverse function, if you wanted to like call this, instead of y, if you wanted to call it like g of x, I might do that on some answer keys and stuff, but whatever. We can just call it inverse if we want. Let's make a table for that one. Here's the cool part. We just saw it on the couple slides ago. Instead of like, not that this one's terrible to plug in numbers for, instead of even doing that, instead of plugging these numbers in here and seeing what you get when you square root them, just literally flip your table over. These numbers all come up top. So 0, 1, 4, 9. 0, 1, 4, 9. And these numbers all come to the y's. 0, 1, 2, 3. Now, again, like I said, this one isn't that hard to tell. Like by plugging a 9 there and square root it, I get 3. But there's potentially ones that are going to be tougher where it's, instead of making 2 separate tables, it's like a 2-for-1 special. So I go to plot them. I get 0, 0, 1, 1, 1, 2, 3, 4, 2, and then 9, 3 is going to be off my graph. We get this. It's essentially, it's our parent square root graph. We should label. I screwed up on the first one. I should have said that, hey, this is, just distinguish. I'm using colors, which makes them stand out a little bit, but most of the time you're working just in pen or pencil. We can just, like I said, call this inverse. That's where it's kind of nice to maybe have it as g of x. But we've graphed the function, f of x, and its inverse. We've labeled them. We've got some tables. The rewrite wasn't terrible. We got it. Awesome. Keep rolling. A couple more. We're doing good. It's actually not a terrible lesson as far as lengthwise goes. A lot of the same concept. Here's one that sometimes people struggle with. So I'll try to make it clear here. hopefully you've heard of the vertical line test, maybe. Like, so just as a recap, before we totally get lost in the horizontal line test, what is the vertical line test? The vertical line test, just if you want to see it, just as a recap of maybe something that you haven't done for a long time, the vertical line test is a test that you can give any function. So like here, I got a bunch of graphs, or anything that basically you would give a relation, a test, to see, is that a function? So is that red circle, does that represent a function? Does this graph represent a function? Does this graph represent a function? Does this graph, let's do one more. Does this graph, or just a line, does that graph represent a function? So we'll come up here, just bear with me here. The vertical line test says if you can draw a line, of any vertical line, and hit your graph more than once, it's not a function. So the circular graph would not, you couldn't get a function to represent that. And it goes back to what we said a second ago, that this input has two different outputs. Okay, these other three I think are going to be okay, right? There's not any vertical line that I could draw that would ever hit this graph more than once. Like I could draw a bunch of vertical lines, but any one vertical line would never hit this graph more than once. So these other three would, yes, be functions. That one would not be. Okay, so that's just a old school recap of something that hopefully you would have seen before. So what the heck's going on with this horizontal line test? It works almost exactly the same way. It does exactly the same way, but it's to test the inverse. Okay, so if this blue graph is if I want to know, is the inverse of this blue graph a function without having to go through the trouble of plotting points and making the inverse, I can just give the original function the horizontal line test and see, oh yeah, okay, that one passes the horizontal line test. Therefore, I know the inverse would also be a function. And we just saw this one a second ago, so it's a parabola. If I give this parabola the horizontal line test, well, I know by hitting it twice here, my inverse would not be a function. And like I said, we just saw it a second ago. It was the graph that looked like this. So if I had that graph and gave that the vertical line test, you would fail. So I know sometimes people get confused, vertical line test, horizontal line test. So the vertical line test is for if you have something and you want to try to see if it's a function without getting like super detailed with points, you literally draw a vertical line. If you hit it twice, it's not a function. The horizontal line test is used to check to see if the inverse of a graph would be, or of a function would be a function. Let's do it here. I've got two pre-made graphs for us that we don't actually have to make the graph, but we're just going to check and see, is its inverse a function? Basically give it the horizontal line test, okay? So we are doing a couple different things. So consider the function f of x equals 2x cubed plus 1. Determine whether the inverse of this graph is a function. So here's what this graph looks like. It's made for us. We don't have to make the graph. Is the inverse going to end up being a function? Without seeing it, without like flipping this over, right? What would the inverse be? It's going to be reflected over this line right here. So this whole thing's gonna get weird and do this stuff here. Like we shouldn't be doing that. The point is, I don't want to mislead us and say we got to do this, because basically all I have to do is give this one the horizontal line test, and if I hit the graph more than twice, these are all just single hits, the inverse would be a function. I know it gets a little bit tight right here, and maybe everybody's looking at that spot right there. Like, what about that line? Right? This horizontal line test, are you sure that's not going to hit those? Those are different points there. I know it looks like it gets really flat in the middle there, and it does. I'm not disagreeing with you that it does look flat, but it's also a cubic function where it turns over at that point. So don't read too much into it. Whoops, that's not a horizontal line. But long story short, this cubic function, so let's say that part first, that the inverse is a function. That's literally all we have to say. I've got my evidence right here. If it asks for a justification, we would say passes f of x passes horizontal line test. All right. So like I said, I feel like I spent already too much time on that. Hopefully that's something that you guys pick up, no problem. All right. Here's kind of the big part of the lesson we talked about already. Now it's actually find the inverse. Okay, so find the inverse of this. We don't have to graph it, but find the inverse of that. So here's our 3-step deal. Replace f of x with y. Y equals 2x to the third plus 1. Switch your x and your y around. So x comes over here. Y comes over here. Whoops, don't lose my third. And get your y by itself. Sweet, awesome, we can do it. Subtract a 1. We've done it now. What, this is 5th, 6th time? Equals 2y to the third. We'll divide both sides by 2. Probably going to have to scroll here a little bit. X minus 1 over 2 equals y cubed. We saw this a little earlier where I'm going to cube root both sides, which is no big deal as far as we don't need 2 solutions here. So if I keep everything just how it is, the cube root, whoops, I forgot my cube root again. I did that earlier. The cube root of x minus 1 over 2 is equal to y. There is our inverse. We found the inverse. So if I actually needed to like come up with some points now, I could plug x values in and I would graph this. It would show up on there, but we don't have to. It didn't say to graph it. It could, but all right, couple more. We're doing all right. Same deal, same setup, same instructions. We got this function f of x equals 2 times the square root of x minus 3. Determine, let's do the first part, the horizontal line test. Determine whether the inverse, without seeing the graph, is going to be a function. Yeah, no problem, right? So it's if we got the graph in front of us, it should be pretty easy to tell. All these horizontal lines only intersect once. So same as the last one. Inverse, we'll write it out. Why not? Inverse is a function f of x passes horizontal line test. All right. Okay, so now the bigger part here, the find the inverse. This one's got one thing we got to watch out for. All right, and it kind of goes back to the previous lesson. So I want to try to make things simple for us here. Whenever I see a square root function, this is going to apply. Okay, so everyone hopefully recognizes this as a square root function. Two things I want to ask you. What is the domain of this function? And it's actually kind of tricky that x's can be 3 and above. So if I'm just taking a step back and looking, okay, yeah, you can plug in a 3 there. 3 minus 3 is 0. But what would be the issue if I plugged in a 2 here? 2 minus 3 is negative 1. I would try to square root negative 1 and I would get an error. So any x's that we plug in here are 3 or bigger, have to be 3 or bigger. Because we can only plug in 3 or bigger, this is actually the more important part, is what is the range? And I know we haven't done a ton with range recently, but we kind of need to see this here for a second. If I plug in that 3, the smallest x value we could ever plug in being 3, right? We just said that. That's going to tell us, and by evaluating when 3 goes in there, what's the smallest output we'd ever get? 3 minus 3 is 0. The square root of 0 is 0. 0 times 2 is 0. So my range is 0 to infinity. Now, we're not going to have to do this every time, but I want to at least give some credence to what I'm about to tell you here. That, okay, my domain is 3 to infinity. My range is 3 to infinity. We actually had the graph, so it's kind of nice to see that, okay, left to right. Left is 3. We're going right forever. And then low to high, it starts low at 0, but then goes up forever to infinity. What did we say? I can scroll back to it. I might as well. That when we come up with an inverse, the domain and range is flip-flop. The domain and range are also interchanged. So because this is the only function that this happens with, is that it's a square root function. So there's a restricted domain and range. So on our final inverse deal, we're going to have a restricted domain, basically. So let's do the inverse part of it first. Because nothing weird happens there. It's just we have to tack on like a clause almost at the end. So I don't mean to. We did all that work and we're like, whoa, what? We're not going to use it. We will in a second here. Okay, let's do our kind of our 3-step deal. Right? Find the inverse. So step 1, just write it as y equals 2 times the square root of x minus 3. Awesome. Simple. Swap your x and your y. X equals 2 times the square root of y minus 3. And then get your x by itself. I'm sorry, yeah, get your y by itself. So divide both sides. Get this 2 out of here, right? Just like before. Get that 2 out. X over 2 equals y minus 3. Okay, now we're set up. Let's square both sides. Undo this square root. Square the whole side over here. So we'll scroll down. So we're sitting on y squared over 4 equals y minus 3. Let's go left to right now, just to finish it. So we're going to add 3 to both sides. So here's my final y squared over 4 plus 3. I've added that 3 to the other side equals y. Before I circle my answer, I guess we could, that is the inverse. But like I said, there's just like a waiver clause on here. What's the domain of this right here? Whoops, I lost track of an x. Darn it, I feel like an idiot. We can fix it. At least I caught it before I stopped recording. I saw those 2 y's there and it looked bad. Right? That I just magically turned that x into a y. So here we go. Y equals x squared x squared over 4 plus 3. So just on by itself, this isn't all real numbers. Like, if you're just squaring numbers, you can square any number you want. But because we came up with this based on this this function that had a restricted range, remember the range of this one now becomes the domain of this one, right? We're switching them. So this one would have a range of 0 to infinity. Would have a domain of 0 to infinity with a range of 3 to infinity. So long story short, we've got to tack on just the domain part of it, that x has to be greater than or equal to 0. That needs to be there with that one. Okay, so we're basically taking this range part of it, and that's what that means, right? When we say 0 to infinity, we're saying 0, x has to be greater than or equal to 0. That's what we're saying there. We got to put that on there. So if you're looking for, like, what do I need to know, Mr. Kroll? You keep talking, rambling. What do I need to know? When I see a square root function, for the most part, I think we're going to have to, like, I don't want to say 100% all the time, but I think for the most part, we're going to have to tack on this x greater than 0 kind of caveat. All right. So it's just kind of one more thing that we got to keep track of and watch out for. But we'll practice it. We'll be all right. Last part. All right. It's a note and then just a one practice example. If we want to confirm, if we want to verify 2 functions are inverses of each other, it's a relatively short process. This is the notation for it. It's called a composition of functions. So it's let f be inverse functions. This is kind of the rule for it. Basically what it's saying is, if you take one function and plug it into the other one and simplify and cancel out all your operations, and it simplifies to x, and then you go ahead and do it the other way, take this function and plug it into this one, and you simplify and you get to x, that's like the confirmation, that's verification that those functions are inverses of each other. So with words, it's kind of like, oh, what? So let's do one here. I think it's a decent one to look at, and then that'll be that. So, all right, verify these are inverses. So there are a few that we could potentially see. I mean, they don't have to be inverses of each other, but it's basically should say confirm either one way or another that they either are or are not inverses. Obviously, I can see a 3 and a 1, a 3 and a 1. So, I mean, I'm thinking they are, but that doesn't always work that way. We can look at examples that aren't. So here's what we should do. Same thing we've done earlier. Like, show your notation. What's going on here? I'm going to do f of g of x. That's how you would say that. And what that means is take g of x, right? Start with the innermost. Take this right here. What is g of x? X plus 1. And plug that into f of x wherever I see an x. Okay, so I'll kind of do it below it here. So I got to kind of peel this 3 off of it. I'm just going to do it re-equals here. Equals, peel that 3 off the front. This 3 right here got peeled off. Now I'm going to use parentheses, and I'm going to substitute this whole thing in there. X plus 1 over 3. And then I pick back up with the minus 1. All right, so that's just kind of the first part, is just get one function into the other. Use the notation f of g of x. And then simplify it. All right, so don't just start crossing stuff off. That's what we can't do. You can't just go this, cross, x. There's multiple things that have to happen here. How would this work? This 1 and this negative 1 can't cancel right now. There's parentheses kind of superseding that subtraction. This multiplication has to happen first. So you could definitely cross off this 3 and this 3, because a 3 in the numerator cancels with the 3 in the denominator. Great, I'm all for that. You could drop this in here and go 3x plus 3 if you wanted to distribute it. I think it maybe makes an extra step, but let's cancel the 3's on the outside. What are we left with? We're still sitting on x plus 1 minus 1. So the parentheses kind of ended up going away because we took care of this 3 that was supposed to be multiplied. We got rid of that multiplication. And then, sure, sitting right now, x plus 1 minus 1. Well, we know what 1, positive 1 minus 1 equals. So this does absolutely simplify down to x. Okay? So a lot of times these problems are just showing your work and taking care of your order of operations as much as anything else. Okay? We're not done, because we do have to go the other way. We said just because it works one way doesn't guarantee that they're inverses. We got to go the other way too. So it's going to be g of f of x. It's weird because there's like that double set of parentheses there. All right, so starting over, I'm going to kind of just clear this off here just so you can see what's going on. We are going to take this function and plug it in right there. So we're going to say, right after, here we go in the numerator, 3x minus 1. You can use parentheses on that if you want. We should, plus 1 over 3. So I'm just kind of picking up on the function here. I got the plus 1 over 3. I just replace that x with this whole function. So again, simplification-wise, it's truly backwards. I can't cancel this 3 yet with this 3. I'd have to put this 1 over 3 and this 1 over 3, which again we could do, but I think it makes more work. So what's the first thing that actually gets simplified here? This minus 1, this plus 1. Okay, so we would be sitting on then 3x over 3, which, sure, absolutely, 3x over 3. I know what that simplifies to. The 3's cancel, just leaves us with x. Awesome. And I say, I'm good. Yeah, I got x over here. I got x over here. These are inverses of each other. That's the work. That's the verification. That's the justification. That's how it should look. Okay, so take care of your operations. So, like I said, just maybe it's helpful to kind of see, because I feel like I see this a lot, whether it's homework, quiz, tests. Hopefully you have all your solutions. Just go back a few seconds and watch it if you need it. People get here and they say, all right, I plugged it in. I'm doing this. Boom, 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 X, done. Yeah, it works out. And you're kind of taking some liberties there, and I don't think that's not how that goes, right? We can't X everything off and just say whatever, it's X. So I want to kind of you to go through and show, what did you do first, what did you do second, maybe what did you do third, right? There could be more operations here. All right, not terrible. Hopefully that wasn't too bad on inverses there. We definitely hit it all, right? I usually like to recap and make sure we didn't miss anything, but we definitely did linear and nonlinear. Finding the inverse, that's kind of our 3-step. That's the biggest one there. Verifying, that's what we just finished with, verifying that we had inverses of each other. And we did do some graphing. Not a ton. We only did one example here, but we looked at, how are the graphs affected, y reflecting over y equals x, using that horizontal line test. That's this part, determining if the inverse is a function. flipping the tables around. So there were some graphing components that we looked at as well. So that's it. 5-6 in the books. Call it. I will see you in future lessons.